Bismillahirrahmanirrahim. Okay, today we'll have a look at Unit 6 of your Paper 1, which is Assembly Language. The agenda of this lecture is that first of all, we just have a quick recap of what assembly language is, what its important essential parts of each instruction is, what this role of assembler is. And after that, we'll start just to take a quick recap over the difference between symbolic addressing, relative and absolute addressing, followed by the overall process of a two-pass assembler and what are the steps that are carried out in each of the two passes mentioned in the two-pass assembler, and how your assembly language instruction that starts off, say, for example, here, such an assembly language instruction, how it starts from there and ends up into something like this over here. So without further ado, let's go. Okay, so basically, we've always studied assembly language as being a low-level programming language. Now, basically what that means is that it's a language that is near machine understanding. And as opposed to high-level languages being near human understanding, these languages are easier for the machine to understand. They're not machine readable right away. They need to be converted into machine code as well. But the thing is, conversion process from assembly language code to the relevant machine code is a relatively simple process, simple and fast process. Okay, since the language that we're looking at right now, assembly language, is near machine understanding, it makes sense that maybe, and most probably, it will be difficult for us to understand. And yes, that is quite true. I mean, we have used assembly language, and this was actually the first, development from machine code that was used for programming before. Now, assembly language was the actual development that was slight improvement of what the options we had before, i.e., the machine code. But when we talk about higher level languages such as Python, Python seems like a much easier language as compared to machine code, or sorry, as compared to assembly code. So despite its difficulty, there are assembly language applications still exist. Most importantly, we may want to write a program where the actions taken in the processor are directly controlled. So the lower the language, the more in touch and more it gives you control over the overall working of the hardware. So if the application that you, or the problem that you're trying to solve involves you getting in touch with the hardware, mostly, yeah, getting closer to the hardware, then you will obviously have to work with assembly language. However, with writing a substantial program as a sequence of machine code instructions will take a very long time. And it would be inevitably lots of errors along the way. The solution for this type of programming is to use assembly language. As well as having a uniquely defined machine code language, each processor has its own assembly language. So we will be looking at a type of syntax that resembles assembly language, and it's actually a different version of assembly language. So anyway, what is assembly language? A low-level language related to machine code, where opcodes are written as mnemonics, and there is a character representation for the opcode. Assembler is the translator that converts the assembly language code into machine codes. Like we remember what the role of a compiler is or the interpreter is. It translates high-level code into machine code. Assembler does the same thing, but this time with low-level code. So assembly language instruction written in assembly language contains two parts. There is the mnemonic. Basically, the mnemonic represents the opcode. And by opcode, we mean what does the instruction do? What are the steps, or what is the basic, action that the particular instruction is taking place? Is it adding? It is loading? It is whatever it is. So that's mentioned in the opcode. And then, as with all instructions, they have to be instructions are made up of two parts. There is the opcode, which is mentioned by using mnemonics, and then there's the operand. Now the operand basically comes equipped, can be written in either an actual address in the memory, or it could be represented by a symbol, or it could be represented by a position relative to the start of the program. We'll be looking at these three methods in just a bit. But one instruction in assembly language is made up of two parts, the mnemonic, which is the opcode, and the operand. So that is what we understand about instructions, that it needs the opcode and operand. That makes one instruction. And this is how assembly language is written. Of course, high-level language use the same format as well. All instructions require the opcode and operand. What is to be done and what is the data that is being used. Okay, using assembly language, the programmer has advantage of coding being easier to write than would have been with machine code. So as mentioned before, it is actually an improvement over the basic machine code. Now, the assembler allows special features that were not available with machine code, which are adding comments, creating symbolic names for constants, labeling of addresses, making use of macros, and making use of directives. Now we'll be discussing these in a little while. We'll try to understand what that macros and directives are. I'll show you a example of what a directive may look like and what possible directives are used by your assembly language. Okay, directive in simple terms is an instruction that is given to the assembler program. So it could be, for example, to load the code, the assembly code at a particular location in the memory. That's a particular directive, that's instruction that you give to the assembler to cause it to take a certain step. Now let's look at what symbolic, relative, and absolute. Now, if we understand these things, we'll try to make sense of what macros are when we come to the two processing. But now, before we move on to any of those, we need to understand the difference between symbolic addressing, relative addressing, and absolute addressing. Now, basically, if I use symbolic addressing, what I'm doing is that I'm, instead of using actual memory addresses, as you can see here, this is one instruction written in assembly. There's a visible space in between these two instructions. This space makes it clear that this instruction is made up of two parts. One instruction will become one part of the instruction is my opcode. The other part is the operand. So as mentioned before, all instructions, in fact, most of, because there's some, special instructions that don't require an operand. But other than that, for example, you see in right here. In doesn't have an operand mentioned in it. That's okay. Same thing goes with out, same thing goes with end, so on and so forth. These instructions don't have operands with them, and yet they are still instructions. But most instructions have an opcode and an operand. And these two things combined together to actually perform some action. Now, as you can see here, I'm actually using variable names. Apart from these opcodes, they're part of my assembly language. The rest of this part, I see the operands that I'm using. The operands are mentioned in the form of actual variable names, identifiers. So for example, we got max, total, count, so on and so forth. Now this is the name of a register, so don't worry about this. But the rest, max, total, count, these are variable names that usually we see in high-level programming, that usually programmers opt to use count, total. Basically, they're defined by the programmer themselves. So in a similar way, I'm using variable names over here. In the world of assembly language, these variable names or these variables or these identifiers are referred to as symbols. And to understand these symbols and what memory location do they refer to at that particular time, a data structure known as a symbol table is maintained to show. So if you talk about count, okay, but for assembler, assembler really needs to know what data count has, and for that it will have to access the actual address location where count's data is stored. So in that case, count won't matter. I will have to have the actual address if an assembler is being used. But for my understanding, making use of count and total and max makes it easier. It makes it more familiar for me. So for the assembler to understand what count you're talking about, what actual memory address are you talking about? Where is the data stored for count in the main memory? Because my assembler will have to use that data for the execution. So it has to know where exactly the data is stored. In that case, my assembler will maintain a data structure known as a symbol table. And basically what it does is that it keeps a record of what variable is saved in what memory location. So if, for example, my assembler will need access the content of count, it will simply refer to the symbol table and see where is count actually located in my memory, the absolute address. And it will access that address, fetch the data, and make use of it during its execution. So this is symbolic addressing. As you can see here, apart from these, now this is immediate addressing, as we've discussed this before in assembly. These immediate addressing means that this value on its own, as it is, will be stored into your accumulator list. Same thing goes with this 48. These are not addresses. But when I'm talking about addresses where data will be stored or where I'm reading it from, in that case, the address can be either mentioned in the real address name that where the data is right now physically stored, or it could be referred to as by a symbol, in which case a symbol table will later be used to identify which location this, for example, count variable is actually being saved. That is known as the symbol table. So when I have the symbol table and this program runs, the assembler will refer to the symbol table and see, okay, you want to access data in, say, for example, total. Okay, that's okay. You will refer to the symbol table, see where total is actually stored right now, access that memory location, store, and do whatever the data, the opcode requires at that particular moment. So this is an example of symbolic addressing. Now let's check out absolute addressing. This one over here. What's the symbolic addressing? Now, as you can see here, my assembly code, as with all programming languages, my assembly code too is a sequential code. Every line is executed in sequence, starting from my first line. And each instruction that you see in front of you, each instructions occupy a different memory location in my main memory. That's highlighted by these addresses. So my address location 200 has this in it, instruction in it, 201 has this instruction, 202 this instruction, so on and so forth. And it goes all the way to 250. So we got 15 lines in this code. This is absolute addressing. Now, why is this called absolute? In fact, if you look closely, this code actually is the exact same copy of this code. Of course, the major difference we see here is that instead of using words like match, total, or count, I'm stuck with using the actual memory addresses like 216, 215, 217, so on and so forth. When I'm actually referring to a memory location by its real address, I'm using what is known as absolute addressing, like so. Now, the benefit of using absolute addressing is one, that you don't necessarily have to go through the process of converting a symbolic address to its absolute address by accessing a symbol table, first thing. Secondly, in fact, that is the only benefit of going with absolute addressing. However, the drawbacks of using for an absolute addressing are also very considerable, and they actually make a huge difference. Now, the biggest drawback for using absolute addressing is that we need to understand the main memory is basically a volatile storage memory. And by that by that logic, it means that the data in my main memory is constantly changing. It also means that my device will be turned off when the power is off and data will be deleted. But that also points out that my data can be adjusted, and it is changing constantly during my computer's time on. Because of which, the data that I'm referring to here, for example, LDM hash 0, sorry, not this one. In fact, add 216. Now, this is actually a memory address 216. But let's just say I want to run this instruction. What this instruction mean is that I want to add the contents 216 with the contents of my ACC and store the contents back in the ACC. That's what the instruction does. Now, at this particular moment, let's just say the address location 216 really does have a value that I need right now. That is relevant to this instruction that I'm using right now. Let's just say that is the current situation. The 216 really does have, at this moment, 216 has the data that I need. But there is no guarantee that after a small time, 216 may hold some other information, because also, as Von Neumann stated, that each address will have one data at one time and some other data can replace it at any time. So let's just say at this particular moment, 216 has the data that I need for completing this instruction, and it won't generate errors. On the other hand, let's just say that after some time, since my memory situation is changing, the data that was previously stored in 216 has shifted to say 316. Now the data that's relevant to the program that I'm running right now is actually stored in 316. Now what that means is that since the data that I was referring to here has shifted to 316, I will have to go ahead and change all of these addresses in the code as well. So wherever I'm using 216 as an address, now it should run 316. And if, say, for example, I only have three mentions of 216, I will only have to replace 216 with 316 only 3 times. That's okay. But what happens when this program assembly code is pretty long? And say there's 100 references to a memory location. What will you do then? Will you readjust 100 instructions where 316 was used? Yeah, 216 was used with 316. Will you do that? That's actually quite difficult. So that's why absolute addressing is discouraged. That 216 that I'm using right now has data that I need right now, but there's no guarantee. After some time, the same data that I was just using right now that was in 216 will now be saved in 316. Now, for accessing data stored in 316, I'll have to change my code to reflect 316 where it used to say 216. And that means every time the situation in the memory changes, I will have to rewrite my code. This is the biggest advantage of absolute addressing. On the other hand, the third method, which is known as symbolic addressing, follows another principle. Now, the basic concept behind symbolic addressing is that, or in fact, let's rephrase that. Symbolic addressing makes use of a very basic fact. And what basic fact is that? When I run assembly language code, all of my instructions will be executed sequentially unless there is a conditional or unconditional jump. If there is no jumping, then my instruction will start from address number 0 and carry out till I reach the end instruction, which basically transfers the control of my assembler back to my operating system. Now, let's just say all of these instructions are located in contiguous locations. And the first instruction is stored at the first address that I am just using right now for my program to run. So basically, what relative addressing does is that it calculates, instead of mentioning addresses with their real names or even symbol names, what relative addressing does is that it, instead of using names, it simply says that address, which is 15 places from my base register. Now, what does this mean? It means that my base register holds the address of the first instruction. So wherever this instruction in is stored in my main memory, the address will be in my base register. Now, if I were to, for example, access this instruction, what is that? What address will that be? Whatever the address that my first instruction got, say it got 317 or 417. Now my first instruction is lying at address number 417. However, this instruction right here, as you can see here, store BR plus 15. Now what that means is that it wants you to store some data into a location that is held at 15 places from my base register. By the way, my base register has the address of my first instruction. So the address of this first instruction is currently loaded in my base register. If I want to access this instruction, I will simply use BR plus 1, of course using the square brackets. If I use BR plus 1, that means one address placed down after my base, the contents of my base register. My base register has 0 in it. One address down will take me here. On the other hand, if I use this BR plus 15, that means I want to go 15 places down after the address pointed out with the base register. So let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, this is from starting from 0, these are 15 places. Now, what this does is subtract 48 and store where the contents of ACC where you want to store the contents of ACC at the address that is 15 places after the contents of base register. So basically this line number 2, is referring to yes, this one, STO max. This is max right here. Likewise, I am also referring to 15, and this is 15 right here. Okay. Now, this is my absolute address that I'm actually using. I'm not using the actual address, but I'm actually calculating my address based on the contents of my base register. So when I want to run this instruction, as you can see, instruction 2 is basically and doing what? Storing the contents of ACC. It means storing of contents of max into ACC. Now, as you can notice here, my instruction after sub 48 is STO max. So that means is that after storing my 15 at my 48th position, after doing this, after subtracting the number 48, and I want to do this instruction in your, what you call it, absolute addressing. By the way, max is 15 places from the start. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 right here, I think, from the start, starting from this place. So right here is max, 15 places from the start. So instead of calling it max, I'm going to say that address that is 15 places from the contents of my base register. And I repeat again, the contents of the base register are actually the address of my first instruction. So instead of saying max, I said BR plus 15, or the location that is 15 places from the contents of the base register. Similarly, BR 16 will be total because I'm accessing the 16th location from my base register. This one will be 17 places from base register, so on and so forth. Now, this is known as relative addressing. Now, the benefit of using relative addressing is quite similar to that of symbolic addressing. Now, let's just say the situation in my memory changes and the addresses that I was using before, for example, I was using 215, will not make sense here because your program has changed, the situation in your memory has changed. And that's quite possible that this entire assembly code has shifted around the main memory. So if I were to remember 215, it's no longer 215 anymore. It could be 315 now. How will I know? You won't, right? So instead of using this method, you can go for this relative addressing method. So what basically it means that if I want to go to say 215, I will assume that my instruction is starting at address number something something, and instead of saying 215, I'm going to say the address location that is 15 places from the contents pointed by my base register. Now, if my max is supposed to be 215, so basically my base register will be pointed towards 200. So basically what I'm talking about is 200 plus 15, which is my max place right over here. I'm actually storing the contents of my ACC into this location, this location in my main memory. Instead of referring to the actual addresses as well as symbolic addresses, I'm actually calculating the address of my memory location on the go by using this formula. Similarly, if you can see here, I'm storing, fourth line means that I'm storing fourth line, 1, 2, 3, 4. I'm storing something in total. Total is actually this place over here, and that is 16 places from the start. Same thing goes where I'm storing something in count, and for that, I will be storing the data in this place that is 17 places from base register. So this is relative addressing. Your address, you're not using an address. This is a conventional method of writing symbolic addresses. You're not doing that. Instead of that, you're simply relying on a calculation that is carried out on the go, on the runtime, for trying to figure out where your data is. So it doesn't use addresses, but it uses the person who tries to access the network or sorry, it uses the concept that my address is being calculated on the go. So I'm just content of what the base register has, and simply I will add these numbers to it to figure out what the real address. Now, again, what a base register holds the address of the first instruction for an assembly program. So let's just say this program will run, my base register will have the value 200 in it, like so. So this is the difference between symbolic versus what you call it, relative versus absolute. Okay, now that we have a slight understanding of how your addressing modes, that is symbolic addressing versus absolute addressing versus relative addressing work. Now let's look at the basic overall process of a two-pass assembler. Now, obviously, but the name suggests that two-pass assembler means that my whole assembly process or my assembler is working in two phases, and each phase or each pass has its own set of activities. So let's look at each of them in the two-pass assembly. For any assembler, there are a number of things that have to be done with the assembly language code before any translation can be done. For example, removal of comments. So if you have added any comments in your assembly code, which yes, you can do in assembly language, then they will be removed first off. Secondly, replacement of a macro name used in an instruction by the list of instructions that constitute the macro definition. Now, let's understand what the macros are for a minute. Basically, a macro is assembly languages alternate to a subroutine. So if you consider the example of a high level language, if I am using subroutines in my high level language, I will be using two steps. The first step will be the subroutine definition that will always be carried out first before I can use the subroutine. So the first step is that I will define the subroutine, and basically I will define its name, its type. Is it a procedure or a function? How many parameters does it take? If it's a function, what type of data it's returning, so on and so forth. After this header, I will start defining the lines that that subroutine will be executing. And that is my subroutine definition. Now, once I'm done with the definition of my subroutine, I could proceed towards the next step, which is calling the subroutine. Now, I only have to define a subroutine once, whereas I can call a subroutine many times I want in my program, main program. So general principle of using subroutines with respect to programming is that it makes your overall code shorter. How? That the subroutine that you defined, you only have to write it once, and all the code that's written inside the subroutine can be repeated any time, a number of times without having it to be written again and again. So one is the procedure subroutine definition, the other is the subroutine calling. There's a lot more detail about this on paper too. Similarly, if I'm using macro, same thing is happening in assembly as well. My macro is the same, is the equivalent as a subroutine in my high level language. I will also have defined a macro before, and then once I'm done defining the macro, I will start using those macros in my main assembly code a number of times. And because of this, the code that was written in the macro definition will not have to come again and again. And I will only have to define it once and simply call the macro repeatedly. So if I have made use of macros in my assembly code, this step simply accesses those macro calls wherever the macro is being called inside my subroutine, and simply replace, macro is being called inside my main program. Wherever those macros are being called in my main program, my assembler simply replaces those macros with the actual code, the definition of those macros. So you're not doing it, you don't have to write it. You only wrote the main code with the macro calls without having to write the definition again and again. But the assembler takes care of it for you. So wherever those macros are being called, the assembler replaces those macro codes with their definition. So making your complete code on the go, right? And you don't have to write the code. Okay, so that's one step that assembler takes. After that, it removes the storage of directives, removal and storage of directives to be acted upon later. Now, what is a directive? As mentioned before, directives are instructions that are given to the assembler to take a certain action. Let's look at some directives, for example. As you can be seen, there are many directives that assembly language uses. But there has been some examples of, for example, this org and the directive that your assembly that's commonly shown in your assembly code. We just saw a few examples. Now, these are examples of directives. Now, let's just say I refer to the org directive. Now, the org directive basically does what? That if you want to load your assembly language or assembly code and in a particular location in your main memory, then you can do that with the org directive. So for example, if you are using org1024, that means that I am loading my code at address location 1024, for example. 1024. Now, 1024 can be written in hexadecimal as well, like this. So basically, org allows us to load our assembly code at a particular location. So I will also show you an example from your past paper where org is being used, and it simply points out where assembly language code is loaded in your main memory. Now, what benefit does that do? Well, let's just say I'm using relative addressing. With relative addressing, my base register will hold the address of my first instruction. So the contents of my base register are determined by this instruction here, by this directive over here. So let's just say that org1024 took place. By that logic, my base register will hold the address 1024 because that will be the address of my first instruction. And if I have that address, every other instruction which is relative to the first address in relative addressing will be easily calculated. So for example, if I have an address, say BR plus 10, then basically that would mean 1034 because the contents of my base register are 1024 and BR plus 10 are referring to 1034. So org helps us do that it starts your instruction, it loads your assembly code at a particular location in your main memory. Similarly, we have this directive, which is referred to as end. We see a lot of this as well. Now, the version that we see in your A-levels code does not have any operand here. So basically, all you see is the end code here. So it's simply end. So it's one of those instructions that do not have an operand. And basically, what it does is that it shows that there's the end. My assembly code has been ended here, and it's basically instructing your assembler to hand over the control back to the operating system. Because while this code was running, control was with my assembler, but now the instruction has been ended. That's why it will cause my control be handed back to the operating system. So this is what this directive does. So just a couple of examples what directives do. We'll be seeing these used in your assembly code as well. Now, directives, since they are actually pre-written, they're not symbols, they're not addresses. They have a specific meaning for assembly language. They don't need any special conversion whatsoever. So they're simply removed from your main code, and they will be used later when instruction is actually being executed. You have to remember that we're still on the first pass. Instruction takes place after the second pass. So in the first pass, I really don't need the directives right now. I'm still trying to make sense of the assembly code, okay? Okay, after that, if this program contains forward references, some instructions may have symbolic address for the operand where the location address is not known at the stage of program. A two-pass assembler is needed so that in the first pass, the location of address for forward references can be identified. And basically, to achieve this during the first pass, the assembler uses a symbol table. And the symbol table kind of like looks like this. Now, as you can see here in the code that we're using right here, we have symbols such as like max, total, count, so on and so forth. And we also have another one. Yeah, start loop. Start loop as always. See? So actually, if you look at it, start loop and max and total, these are different symbols. My symbol table will be basically telling me these addresses are actually what place from the start of my assembly code so that they can be used with respect to relative addressing and their actual address can be calculated. So let's just say, as you can see here in this max, it says plus 15. For max, it's plus 15. Now what that means is that when I'm referring to max, for example, this is max. If you look closely, if this is my start of my program, this is my max. Notice how many spaces have to come down from here to here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So that means that let's not call it max. Let's call it the address that is 15 places from the start of my program. And if I have a base register, which I will, the base register will have an address. And if I add 15 to that address, I'll end up to this place that we're calling max right now. And see how simple it becomes to calculate the actual address. All you need to know the starting address of my program, where it's loaded, and the org should help you with that. Once you have the address of the first instruction, I can simply add 15 places to it to get this address right here. Because if you remember, max is the word I used to make this code more readable. But my assembler will don't understand what max is. It really needs to know the actual address in the memory. So for that, it can calculate it could identify where the start of my program is in the base register and add 15 places to that to reach this position that we're calling max right now. Same thing goes with total. As you can see here, total is one place after max. That's why it's plus 16. So I want to access total. I can simply add 16 places to the contents of my base register and I'll reach total. Same thing goes with your count. Count in 17 places from my start. Yes, it is 17 places from my start. And finally, I have start loop. Right? In the book, it says 7. It's wrong. It's not 7. Let's count out where start loop is. This is start loop right here. 1, starting from here. 1, 2, 3, 4, 5, 6. So start loop is another symbol that I'm using in this symbolic addressing written code. But actually, what is start loop? It is this address right here, this location. What is this location? This location is 6 places from the start of my program. So as mentioned before, start a program is highlighted by base register. I add 6 to that base register and I will actually get to this address. So using this symbol table, as you can see, I have very easily, or not me, but the assembler has very easily figured out what these actual symbols represent in the memory, because that's what my assembler needs. It needs those actual addresses, and that's what the CPU will need as well. The actual addresses, the actual locations where the data will be fetched from. So this is the purpose of your symbol table right here. Now, once I have identified my symbol table, I will move on to my second pass. For the second pass, assembler uses a symbol table and a lookup table. This is my lookup table. Now, the lookup table simply identifies the binary opcodes for each mnemonic. So if I'm using these opcodes in some STO, their binary representations are mentioned here. I have the binary representations of my opcode here. I have the numeric values of my symbols here. I can combine both of these together to form a machine code instruction. Now let's see how that comes up. So let's just say this is my instruction written in symbolic addressing, and this is my instruction, the same code written in machine code. Now, how did I get from here to here? Let's figure out. As you can see here, I got a special instruction in the start that looks like an instruction without an operand. Okay, agreed. It's just an opcode. So according to my lookup table, the binary sequence for in is 0, 0001, tetra 0. So did you see in is replaced by simply 0001 and tetra 0. And after that, I got sub hash 48. Now my instruction set of this computer states that I am allocating 1 byte, you see 1 byte for my opcode, and I'm allocating 2 bytes for my operand. So the instruction format is important here, because if I don't define what part is opcode, what part is operand, my processor will never be able to figure out the operand from the opcode. So instruction format has to be defined. So in this particular processor, the instruction format is defined like so. To the leftmost, the most significant 8 bits refer to the opcode, and the the 16 bits that follow are referring the operand. So this is my example over here. As you can see here, sub is represented by this opcode according to my lookup table, and followed by 16 bits for operand. Now, as you can see here, this 48 is an actual value. How do I know this? Because hash means immediate addressing. And by hash, it means that this is not an address. This is an actual value. And this actual value is to be used, or in this case, will be subtracted from the contents of the ACC. As a result, will be stored back in the ACC. But when I see hash, it means I'm actually using this exact value. I'm not using an address, this exact value. And this is my operand. So in that case, as you can see here, my operand states 48 in binary. And this is exactly 14. This is it. This is 48 represented in 16 bits. Check this out. Is this 32? No, sorry. Yes. Is this 32? Yes, it is. 32. Is this 16? Yes, it is. So 16 and 32 is 48. So as you can see here, these 16 bits very accurately represent 48. Now let's check this out. It says STO max. So as mentioned before, I 8 bits for the opcode. So according to that, STO is represented by this binary sequence in my lookup table. 0, 1, 0, 0, 0, 1, 0. So do I have the same opcode here? Yes, I do. Binary sequence is the same. So that's for STO. Followed by max. Now max, what is this value max? As you remember, in my symbol table, max is actually 15 places from my start of my program. So basically this 15 has to be represented as an opcode. So that's why I'm representing 15 here. So this is the binary sequence for 15. 1, 2, 4, 8, that's 15 in 16 bits. Similarly, I'm using LDM hash 0. Now, as you can see here, the operand is 0 and 16 bits are mentioned here, all zeros, because the value is 0. But LDM, on the other hand, LDM has to be represented according to this binary sequence mentioned in the lookup table, 0010 0001. So 0010 0001, like so. After this, I've got STO total. Of course, STO's binary sequence mentioned in the lookup table will be here. Total, on the other hand, will be 16. Now, how do you know this? Because total we just calculated as 16 in my symbol table. So that's why it says 16 here. This is the value of 16 measured in 16 bits. Same thing goes with STO count. Now, as you can see here, the same code for STO that was used before is also being used here. But count, on the other hand, is not 16, in fact, it's 17. And we just calculated that in our symbol table, the count is 17. Finally, I take an in, and in is again a code. The code for in is we used it before, we use it again. And then for we got sub. Now sub is hash 48. Again, we're using the same method for 48 here. Just is the same binary code. Add total. The opcode for add is mentioned here, and total is actually 16. Total is 16 as we use right here. So same 16 values here. STO opcode and then total 16. LDD opcode and count 17 plus 17. And then we got increment ACC. Now this is interesting. Even though I have increment and followed by an operand ACC, this is a special type of instruction. Increment ACC is a special type of instruction. Why? Because as you can see here, store to count, store total, store max, LDD count, all of these instructions have operands. Total, count, so on and so forth. And even max as well. These instructions have operands which are actual memory locations. These are addresses. Total is an address, count is an address, max address, start loop is an address. These are all addresses. On the other hand, increment ACC has an operand which is not actually an address. ACC is a register. So that's why increment ACC is a special type of instruction in which the operand is not an address. It's not a value like this. In fact, it's a register. So that's what we're doing here, it's a register. But you notice here that my increment ACC, even though it has an ACC operand, there is no such mention of an operand here. And there shouldn't be, because ACC is a register, it's not an address. I mentioned addresses and values here. So it should not be treated the same way. However, this opcode, increment ACC, this opcode is enough to represent increment ACC. Just this single opcode is alone enough to represent increment ACC. Now, this leads to us to a question. You can also do increment IX, increment index register, increment IX. That's also possible. Now, what would I do when I am using increment IX? Since I'm not allowing for operand, how will I differentiate between increment ACC and increment IX? That's a big problem here. But the answer is that obviously for increment IX, the opcode will be different. So just based on the opcode, we should be able to distinguish between increment IX versus increment ACC. No need for operands. The sequence will change for either one of them, increment ACC versus increment IX. Okay, next we'll come here to compare max. Okay, now max, as you mentioned before, as an operand, is an address, and it's 15 places from my startup program. So that's why CMP opcode binary version compared from the lookup table, and this is 15 right here. Then similarly, we got JPN start loop, JPN opcode from lookup table is mentioned here. And start loop, as I corrected before, is not 7, it's 6. Is verified further, but it's also mentioned 6 over here as well. So they accidentally made a mistake by mentioning 6 here. But as you can see here, they're actually using, sorry, they mentioned 7 here where it should have been 6. But we can see here, they're making use of 6 here as it's supposed to be. So JPN start loop, how JPN opcode over here in binary from lookup table. And we got 6 here plus 6 here mentioned in this opcode. Apart from that, and the opcode for and, sorry, the binary version is sequence for and is this. And as that's why it's mentioned as such over here. This is and. Max, total, count. Right now, there's nothing stored in these addresses, so that's why they got nothing. Though there are no values in max, total, count, and when the code runs, then these values will change. So this is how your addresses or your assembly code is translated into machine code. Now you notice that each line written in assembly code is translated only one line in machine code. Always. So if I've got 10 lines in assembly code, the resulting machine code will also be 10 lines. As opposed to say high level programming, if I have one line in high level language, that may result into 2, 3, 4 lines of machine code. But that's not the case with assembly language. The translation process translates one line of assembly code to machine code. So that's why the translation process from assembly to machine code, not only is it faster, it's actually quite simple, straightforward as well. One line is translated from its lookup table and the operand in binary, and that's it. You converted your entire assembly code into machine code. Some points to note are as follows. Most of instructions have an operand, which is 16-bit number. We already know that. Usually this represents an address, but for sub LDM instructions, the value is used. We also know that wherever hash is being used, the operand, the actual value of the operand is being used. Where hash is only referred to your immediate address. Okay, after that, there is no operand for in and end instructions. Increment instruction is a special case. There is an operand in the assembly language code, but it just defines a register, identifies a register. So as we can see here, we saw INC ACC, just the register. However, in the machine code, the register is identified within the opcode, so no operand is needed. So if I were looking at another register, say IX, the opcode will be different for INC IX. So we can just take care of it just by the binary version of the opcode. Okay, machine code has been coded with the first instruction occupying address 0. So let's just say the first instruction starts from address 0 and every other instruction is relative to the first instruction address. So basically you got 15 plus 17 plus 6, so on and so forth. Finally, changes will be needed for the addresses when the program is loaded in memory, ready for its execution. So basically when the program is loaded in the memory, the starting address will be based on the org directive. The starting address, wherever the program lands up in my main memory, the starting address will be loaded in my base register. And I will be able to, based on my symbolic symbol table, I will be able to use this code without any modifications wherever it's loaded in the memory. Because I am simply calculating the actual addresses relative to my start position. Now, since I'm very clear about my start position, thanks to my base register, calculating the other addresses will not be a problem. Finally, 3 memory locations follow the program code have been allocated value 0 to ensure that they are available for use when the proper program has been executed. So in simple computing, programming science, programming and coding terminologies, these 3 variables have been initialized with 0, and they will be changing their state as the program executes.